Welcome to 26th class meeting of EECE574, the graduate level probability and random processes. We don't have much to announce this time, so I will directly review what we learned last time, and we'll have a very short preview, and we will delve on the complex random processes. So during the last two class meetings, we learned what is a Poisson random process and what are the definitions related to Poisson random processes. So the first one was the definition of a counting process. And counting process can be called arrival process sometimes. And the number at a certain time instant is the total number of arrivals or the number of counts up to that time instant. So it could be a discrete time random process or a continuous time random process. What are commons is that they are always non-decreasing because we cannot have -1 count, or we cannot subtract. We always increase. So each sample path of a counting process looks like a stairway, but its length of each step may be different. However, the height is the same if we assume only a single arrival is allowed at a time instant. But that is not necessary to define a counting process. However, in most of the continuous time counting or arrival processes, we assume for convenience that only a single arrival occurs at a time instant, so that our sample path, it could step very fast, but only a unit step jump is allowed in the sample path. So we have a definition of counting process. And interestingly, after we define a counting process, we could derive two related random processes. Both are discrete time random processes. However, if the original counting process was a continuous time counting process, then the arrival time process, not arrival process, arrival time. So let me just say counting process and arrival time process. The arrival time process is continuous discrete time random process if the original counting process was a continuous time process, something like that. And also we can define inter-arrival time random process. So let me modify. So not arrival here, okay, because it's confusing. So counting process and arrival process and inter-arrival process. So inter-arrival process then can be defined as the as something like this. If we define this as the arrival time instant of the nth arrival, something like that. And there are interesting group of inter-arrival random processes that have accents IID. Of course, since this is an inter-arrival time process derived from a counting process, this accents are non-negative with probability 1. Actually, we have to say that if we do not allow simultaneous arriving, then this accent is strictly positive with the probability 1, something like that. And if they are IID, then what do we say? This process is a renewal process. The problem is that sometimes we call the original counting process as a renewal process, even though the definition of renewal process is based on the inter-arrival process derived from the counting process. Now let's go back to our counting process again. And then we may choose two time instants, T1 and T2, assuming T1 less than T2. Then on each interval, we may define a random variable that is the subtraction of n of T1 from n of T2. This is called the increment on the interval T1, T2. And in terms of these increments, we may define that a counting process satisfies independent increments in the case that given non-overlapping two time intervals, the associated increment and increment are independent random variables. In that case, we say independence. And sometimes we call the increment is stationary when the distribution, the random variable n of T2 minus n of T1, this distribution, of course, is a function of, in general, T1 and T2. However, if it is parameterized by T2 and T1. So T1 and T2 affects the distribution only through T2 minus T1, then the increment is called stationary. Got it? So whenever we talk about stationarity, we have multiple time instants and we shift them all with common capital delta. But if we have two time instants, then we talk about the time difference only. Got it? So you remember the Y-sense stationarity and stationary to order 2. Anyway, so increments may be independent, increments may be stationary. However, these increments can define not only for counting process. Sometimes it can be defined for any random process. So we have a more general definition called the Levy process. Now, a random process is a Levy process if it has independent increment and a stationary increment. But x2 minus xt2 minus t1 can be negative. Okay. So okay. It could be 1 if it is a counting process, but it's not restricted to always increasing. The most representative Levy process was what? The Wiener process. As a special Gaussian random process. Of course, we have a counting process that is a Levy process. That is the Poisson process. Now, there are many ways to define Poisson random processes, but in our textbook, we have two definitions. One in terms of the increment. The other is about the inter-arrival time process. The first one is that we have first n of 0 equals 0. And what is the second one? What is the second one? And what is the third one? No arrival. That is not that important. What was that? What was the second one? Independent increment. What about stationarity? Stationarity can be, it's not necessary to be specified here because we just need to define this as a Poisson random variable with some rate lambda. So T1 and lambda 1 and n factorial. Something like that. And we can show that the increments are stationary. Anyway, from these three description, we can derive the first order PMF, second order PMF, any nth order PMF. And at the same time, we can show that the increments are stationary. So this is the first way to define Poisson random process in our textbook and most of the regular textbooks, graduate level textbooks on random process. The second one is that the inter-arrival process is an exponential random variable. So we have the inter-arrival time defined as S sub I minus S sub I minus 1 follows the exponential random variable. Not only this exponentiality, but also we have what? IIDness of these random variables. You could, by the way, we have to have, so this is for I greater than 0. And of course, x0 is defined as 0 for convenience. Yeah. Anyway, so you could show that the first definition implies second definition and vice versa. That is very important. And I believe you've seen one of the proof in the homework. Anyway, so after we derive the first order, second order, any nth order joint PMF of Poisson random process, we could derive the mean path and the autocorrelation and autocovariance functions. Interestingly, what was the shape of the mean path? Very simple. So T and mu n of T. What is the slope of this line? That lambda appearing here. So mu sub n of T equals lambda T. And as you see, and let me remind you, here the exponent must be unitless, but T has unit in seconds. So lambda has unit in per second or hertz if you want. Okay. And again here, since x is x has unit time in seconds because it represents inter-arrival time. So again, x in seconds, so lambda in hertz. And as you see, not only from these two, but also from this one, you can easily see that lambda really means some rate, the slope over a linearly time varying function. And this is called the average rate or average arrival rate of, for example, customers or events. Okay, so if you have some T0, your expected number of arrivals is what? Lambda T0. So the arrival rate, the term perfectly makes sense. What about the autocorrelation and autocovariance functions? You can derive these two functions from the simple property of Poisson random variables. And you can show that the autocovariance function is not a function of T minus T2 minus T1 or T1 minus T2. So what's the trouble? This is not just Wisen stationarity because you don't have constant mean. And also, even after you subtract this mean path, still you don't have Wisen stationarity. So it's not covariance stationary. It is not Wisen stationary. It is not covariance stationary. Anyway, Poisson random processes are very simple to describe because it has only one parameter. So this arrival process model has been used in a lot of analysis because it's simple. The problem is that it's too simple, so sometimes it shows strange property. And if you take graduate level queuing theory course, first 1/3 is usually all about the Poisson processes. You will see some very strange behavior. So very strange claim like this, given some conditions, something is independent, blah, blah, blah. And that really contradicts. And when I took the course, I suffered a lot because it was so contradictory. If we just take a look at the sample paths of a Poisson process, it looks very good. It really well models or approximates the reality, apparently. However, based on my day-by-day experience, this Poisson model of arrival process has some problem, actually. However, there are many ways to overcome that kind of difficulty in engineering. What do we do? Sometimes we make our arrival process to have property very close to our mathematical model by doing some pre-admission process. For example, if you go to a club in Hongdae, what happens? There are gatemen, right? And they control so-called arrival process, right? Similarly, we can do that. We may randomize the arrival time so that after that randomization, the process really looks like Poisson. And that randomization does not much affect overall performance. Then we can easily parameterize the process as a single parameter lambda. And then we can do any analytical analysis and we can optimize something like that. Got it? So good thing for engineers is that we can make the system, especially for communications engineers. What is the most different thing between signal processing and communication is that in signal processing, we have a source and its output to be processed by our system. And then we generate some results. So we build estimators, detectors, sometimes neural nets. We train them so that it could perform as a good estimator. But in communications, the story is a little bit different because initially we are given a channel and we design not only the receiver part, but also the transmitter part so that for example, waveform that passes through this channel really well matches to the property or characteristic of this channel so that we can better easily design the receiver or something. So we have joint design in communications. And you will never forget that. Because sometimes, given a standard, wireless standard, we usually design the receiver. In that case, it's like, hey, even though I'm a communications engineer, I'm always doing signal processing. However, sometimes you just face a brick wall. You cannot improve your performance. You can only do trade-off research. You are frustrated. What do? Just modify the transmitter. Sometimes slightly modifying the transmitter gives you a lot of performance gain. In some cases. Right? Anyway, so that is all about the review. And let's move on to our section 6.7, complex valued random processes. So sometimes it is called complex random processes because we have sometimes real valued vector process, real valued scalar process, complex valued vector process, complex valued scalar process, and sometimes they want to use this valued to emphasize the difference. For example, complex vector valued random process. They do not want to say complex valued vector valued random process. So some people just say complex random process, meaning the each value at a specific time instant of a sample path is a complex number. Anyway, so based on the sample path, the story is very simple. Your sample path can take a complex value at each time instant. So I cannot just simply draw the sample path because it's complex values. In that case, I may say that, hey, okay, I have a real part and the imaginary part. By the way, if you have a complex number z, that is a plus jb, where ab are real numbers and j is the square root of -1, real part of z is a here, and imaginary part of z is not jb, but b, okay? So your real part becomes z plus z conjugate divided by 2. Your imaginary part becomes z minus z conjugate divided by 2j. Got it? So never forget that. You may say that, hey, it's too simple, but it's very important trick to rewrite the real part operator in terms of the argument and its conjugate, and the imaginary part operator as the argument and its conjugate. So based on our observation of this sample path, you can easily see that a complex valued random process is actually what? Two real valued random processes. It's very similar to the idea of a complex valued random variable. At that time, I said that just consider a scatter plot of a complex random variable. And you must draw two axes and put the dots, right? And that is what? That is a two-dimensional random variable or a two-dimensional random vector, right? So never forget the equivalence between a complex valued random process and two real valued random processes. So here goes the definition. So in terms of two real valued random processes, a complex valued random process is defined as what? The summation of two real valued random processes, but with weights 1 and j, the square root of -1. And in order to fully characterize this one, what do we need? We need what? First order, second order, third order, fourth order, any nth order joint CDF of these two random processes. So we must be able to fully characterize these two real valued random processes in order to fully characterize this complex valued random process. Got it? Of course, we may have a major theoretic definition like this. Given an underlying probability space that is fully characterized by the sample space, event space, and probability measure, we have a mapping rule that maps each outcome S into what? Into a complex valued sample path. So you have an ensemble of complex valued continuous time or discrete time signals. And what would be the extension of Kolmogorov's existence theorem? As far as we can describe consistently any nth order joint CDF or PDF, PMF or characteristic function of two random vectors taken from the random processes, then what? There exists this strange mapping rule from sample space to into the ensemble of complex value sample paths. Got it? Now, again, we can define the stationarity of a complex valued random process. And as you remember, because a complex value random process is equivalent to two jointly distributed real valued random processes, what would be the stationarity? What would be the stationarity of order 2, order 1? Actually, stationarity of order 1 may require what? Stationarity of the real part and stationarity to order 1 of the real part and stationarity to order 1 of the imaginary part. Because you can take only one sample, right? What about stationarity to order 2? Now you can take two samples from real part or two samples from the imaginary part or two samples, one from real part and the other from imaginary part, right? And in this way, you can define the stationarity as you define stationarity of a complex valued single random process. Now, we can also define strict sense stationarity if real part and imaginary parts are jointly stationary to any order n. From the second, let's take a look at the first order and second order moments of the complex value random process. So given a complex value random process Z, we may take the expectation of it. At each point t, we have a complex valued random variable. So this expectation can be computed by what? Two-dimensional integration on R2 or integration on Z-plane. And fortunately, since Z is a summation of x plus jy and expectation is a linear operator, we have what? The mean path is simply the mean path of the real part plus j times the mean path of the imaginary part. Got it? So this is simple. What about the autocorrelation and autocovariance function of a complex value random process? Here comes the difficulty as we've seen in our complex value random variable. Because ordinary extension of ordinary correlation does not fully provide all the second order information. And let me remind you, suppose Z is a complex value random variable, then Z is equivalent to this two-dimensional real random vector. And at least this has a mean vector and covariance matrix. The problem is that if you just take the correlation in this way or in this way, what happens? Let's take a look at the natural extension of our second non-centralized second order moment of a complex value random variable. Because modulus of or absolute value of a complex value random complex number squared is simply the real square plus imaginary square. We have what? We have the summation of these two. So if you just take a look at this one, there is no cross correlation. Now let's see the upper one. What do we have? Since z squared is x squared plus 2jxy minus y squared, we have rxx plus 2j rxy minus ryy. One good thing is suppose that you are given two numbers that represented in this way. This is real number, and that is in general a complex valued number. Now, interestingly, if you add two real parts, what happens? just take a look at real parts only, and you add up. You have 2 times the second order momentum of the real part. If you take the real part and subtract them, you have 2 times the imaginary part's correlation. What if you take the imaginary part of this second order moment? You have 2j times the cross correlation. So as you remember, and as we've seen already from our experience, we can immediately see this definition of autocorrelation. And that definition of autocovariance may not fully provide us the second order information, temporal information. That's why we define complementary autocorrelation function and the complementary autocovariance function. Sometimes people say them as pseudo-autocorrelation and pseudo-autocovariance functions. There are many different conventions, but I prefer this convention where I put conjugation on the right-hand side when we have 2 terms, 2 factors inside. And usually, I prefer put plus tau on the factor that does not have this conjugation. So right factor has conjugation and left factor has plus tau, so that they get even, something like that. That's that's the way I remember. The reason why we put conjugation on the right side is that if we extend the idea to a complex vector-valued random process, we want to generalize this autocorrelation and autocovariance functions to matrix-valued autocorrelation, autocovariance functions. In that case, this conjugation becomes Hermitian transposition. And we have vector and vector, so that we have an outer product between these 2 vector-valued random process. You will see soon, okay? Anyway, here comes the Y-sense stationarity. And unfortunately, this importance of the pseudo-autocorrelation and pseudo-autocovariance was not known until around mid-1990s, when I was a graduate student. Before, most of the textbooks, even Peebles' book, only talks about so-called ordinary autocorrelation and autocovariance functions of a complex valued random process. The author, Professor Emeritus Peebles, do not talk about pseudo-autocorrelation and pseudo-autocovariance. The problem is that people did research even before they realized the complementary autocorrelation covariance functions are important. They found it very difficult to have full characterization of a complex random process. So they defined Y-sense stationary complex random processes, but only in terms of ordinary autocorrelation. So the first definition, first definition of Y-sense stationarity of a complex value random process talks only about the mean path and the autocorrelation function. They say that mean path is constant for all t, and autocovariance function or autocorrelation function is a function only of tau. So they did not talk about complementary autocorrelation or autocovariance. So it was somewhat ill-defined. Later, some people modified in their research paper and said that, okay, I define the Y-sense stationarity of a complex valued random process equivalent to joint Y-sense stationarity of real and imaginary parts. In that case, the joint stationarity, if you apply it to x of t plus j y of t, then you have what? You have not only the uh, autocorrelation or autocovariance, but also the complementary autocorrelation and autocovariance functions only of time difference. And this is exactly the joint stationarity of two real random processes. So I myself prefer the second definition. That is same as the third definition. So be careful. Even though I said definition 1, 2, 3, 1 is different from 2, 3. So definition 1 is different from definition 2 and 3. Got it? But as I told you, since this use of ill-defined terms so long a time, so people, some people say this is second order stationary. But that is also confusing because second order stationary sounds like stationary to order 2. But it is not necessarily stationary to order 2 because it talks only about the moments, got it? Expectations. So some people, some old people say Y sense stationarity and second order stationarity. But these days, we just say this is Y sense stationarity and this is, well, strange definition. Got it? Because the complementary autocorrelation can have any arbitrary property. Not any, but very strange property. Got it? Now, let's talk about two complex valued random processes. And eventually we will talk about many or n complex valued random processes. In that case, we can put them together in a vector, right? So this is midway to some notation like this, defined as z1 of t, z2 of t, zn of t. Ready? When I was a graduate student, if I talked about vector-valued complex random processes, many colleagues, friends, classmates maybe laughed at me. But suddenly, this became very important because of the advent of the MIMO system. The MIMO system view a wireless channel or communication channel as a multiple input, multiple output system. Now, what is the simplest multiple input, multiple output system? Input is a vector, output is a vector. What is electrical engineering version of that? Input is a vector-valued continuous time electrical signal, and output is a vector-valued continuous time electrical signal. What would be the communication engineer's version of that? Input is a vector-valued, complex-valued random process. Output is vector-valued, not only vector-valued, but also complex-valued random process. Why? Because in wireless communications, one of the most important way to do wireless communication is to use radio wave. And radio wave can be simply viewed in a radio channel, a real valued bandpass signal. So each input to the real world radio channel for a MIMO system is what? A real valued bandpass signal, real valued bandpass signal. So input is a collection of a real valued bandpass signal. But it's very hard to handle sometimes these signals because it's a bandpass signal. So we find equivalent complex valued signals. So eventually we have complex valued vector random process and complex valued vector random process out. Got it? That's why this is important for communications engineers. Anyway, so we define cross-correlation and cross-covariance functions like this. The only difference is that now you have Z1 and Z2 or Zi and Zj. And here goes the conjugations, and here goes the additions. Got it? Also, we need complementary or pseudo autocorrelation and autocovariance functions without conjugation. Now, what would be the definition of joint wise and stationarity of two complex valued random processes? So suppose Z1 is X1 plus JY1. And Z2 is what? X2 plus JY2. Now you want to talk about joint wise and stationarity of two random processes Z1 and Z2. What would be that? Then you have to remember the cases like this. What was the definition of joint wise and stationarity of four real-valued random processes? And as far as you remember, we never defined that except the two joint wise and stationarity of two random processes. Yes, that is exactly the definition. So if these four real-valued random processes are jointly wise stationary, which means that if you choose two of them, they are jointly wise and stationary. Then we may say G1 and G2 are jointly wise and stationary. Got it? Of course, of course. Otherwise, it does not make sense. Now, we may further extend the definitions. So what about uncorrelatedness? What about orthogonality? They are exactly the extensions of the uncorrelatedness of two random vectors and two complex random vectors, uncorrelatedness and orthogonality. So you have uncorrelatedness of four random processes. You have uncorrelatedness and orthogonality of four random processes, two real parts and two imaginary parts. Got it? So whenever you have confusion, just to go back to the fact that a complex number is simply a two-dimensional vector. Now, final topic. Complex valued vector random process or complex vector valued random process. It depends on which part you want to emphasize. Got it? So you have now Z underscore T. Of course, not many people use in their lecture note this notation with underscore because they can use better typesets, boldface, block bold, something like that. But I prefer still using this one because when I write, it's hard to use boldface or block bold. So I just use underscore. And once when I submitted a research paper, when I used this one of the reviewers really hated that. And the review comment said that, okay, paper's good, but I do not like this underscore thing in representing the vector, something like that. Anyway, so I had to change a lot. And it gave me a lot of headache because I wanted to have like this. Vector means underscore. Bold means a capital means random. Uncapitalized means sample, something like that. Bold means some other thing, blah, blah, blah. Really hate it. Anyway, so first, here goes the mean path of a vector-valued complex random process. Very simple. What about autocorrelation? As I told you, expectation of Z of T plus tau times Z of T Hermitian transpose, right? So if Z is a one-dimensional complex random vector, we go back to our definition of autocorrelation function. And we again have complementary autocorrelation function. Similarly, we have autocovariance function and complementary autocovariance. Of course, you can use T1 and T2 to define this one. And that is sometimes much more straightforward and important. However, if you want to work with Y-sense stationarity or something, anyway, T plus tau and T gives you a better representation. So let's see the case. So what about, not this, what about the Y-sense stationarity and covariance stationarity of a complex valued random process? So I didn't wrote here, but from here, Y-sense stationarity means what? Mu sub z is some constant vector for all t. That is the first. What would be the second one? The autocorrelation function is a function only of time difference. And what else? Complementary autocorrelation. So I put tilde here. Is also function of time difference. Then we have Y-sense stationarity over complex vector valued random process. Interestingly, you can easily show from this definition that any two elements, two entries of Z are what? Jointly Y-sense stationary complex random processes, two complex processes. Pairwise Y-sense stationarity you have. Now, there is a special class of complex valued random vector random processes. That is again what? As we've seen in complex valued random vector, we have propriety and impropriety. So recall that this is the set of all complex random vectors. And there is a very small subset, but let me just divide into two. Here you have proper complex random vectors. And here improper complex, or simply improper random vectors. Or if you say random variables. Similarly, we have what? We have set of all complex vector valued random processes. Again, we have proper and improper. Got it? And what was the propriety of a complex random vector? It's covariance matrix, complementary covariance matrix vanishes. What does that mean by vanishes? Is a zero matrix. Okay. Now we extend it for complex random vector. Same as before, we talk about what? The complementary covariance function is zero for all t and tau. Okay? So t plus tau, t equals zero for all pair of t and tau. C tilde of sub z of t plus tau comma t is zero for all t tau. So what about Gaussianity of a complex random process? Since due to the equivalence between a complex number with two real numbers, you first need to define a Gaussian, complex Gaussian random process. In what sense? You have two real processes. If they are jointly Gaussian random processes, then you have a complex random process, Gaussian. What about propriety of that complex Gaussian random process? Your complementary autocovariance function vanishes, right? And what about complex valued Gaussian random vector process. Again, your complementary autocovariance function vanishes. Got it? In many cases, we have a zero mean random processes. In that case, we may say that the complementary autocorrelation function vanishes. However, precise definition of propriety involves the covariance function. So in this case, autocovariance function vanishes, means proper. Got it? If you take, for example, my course of digital communication, which almost never offered, strangely, in post-tech. By the way, I never taught undergraduate digital communication since I joined post-tech 20 years ago. Strange, right? Anyway, I usually talk about why this propriety is important for communications engineers. And I will not talk much about it, but that may appear in your final exam. So I give you a hint. Okay. Suppose we have a communication system, radio communication system. And as I told you, in radio channel, everything can be modeled as a real valued bandpass signal. Now, suppose our noise or interference can be modeled as a real valued bandpass signal. Now, what would be the property of that real valued bandpass noise? Is complex baseband equivalent. Interestingly, it is proper. Right? So real bandpass Y-sense stationarity implies complex baseband signals propriety. It is proper random process, complex random process. So in many cases, ignoring the complementary autocorrelation worked. No problem in communications. However, they missed one thing, because some man-made signals, like BPSK signal, some MSK signal, like a second generation GSM, that signal is what? Even after converted to complex baseband equivalent signal, it's improper. So if you just process the signal containing improper man-made usually signals using only a linear filter, then you have inferior performance. And that was one of my old topic and long-standing topic in research. Anyway, so we've covered surface, we scratched just surface of this complex valued processes, and more detailed definitions and properties, you take graduate level courses. I sometimes, in every 4 years or something, I offer graduate level special topics course on complex random processes. Anyway, so let's move on to the section 6.3, where we talk more about these correlation functions. As I told you, one of the reasons why we talk about just expectation of something, random process, is because what? It is very difficult to fully characterize a random process. So just take it as a true. Whenever you model a random process, it's a simplified model. Okay? Unless it's the model's reason has very solid foundation on physics, like white Gaussian noise. White Gaussian noise is really white Gaussian noise. It is due to what? It's based on physics. When we have a conductor that has grids of atoms and free electrons, what happens? Free electrons are not free. It's similar to Tesla's full self-driving. It's never full self-driving. Similarly, free electron is not free. What happens? If they are really free, if you apply a voltage difference, what will happen? The electron must move with what? Constant acceleration, right? because it's free. However, what happens? It moves with constant speed. Not exactly, but on average. What does that mean? There is resistance. So always you must be careful. Don't be fooled by those full self-driving, autopilot, that thing. I heard recently a news that the prosecutor's office in the US Department of Justice has started to investigate Tesla because they are talking too much about full self-driving, autopilot, even though that car, of course, it's a nice piece of work. However, it's never full self-driving and autopilot. I heard that the Germans, they are very restrictive, right? Germans, from the beginning, forbidden for Tesla to use the German version of autopilot at all, because it's not autopilot. It's just driving assistance system. Anyway, okay, let's go back to our topic. So whenever we model a random process, it's a model. Got it? So never just say that, hey, this model is too simple. It does not reflect the reality. But as far as it is better than nothing, it's a good model, okay? You have a lot of room to improve. That is a good thing. That is not a bad thing. Got it? However, you must remember it's a model, usually with only a few parameters. Got it? But sometimes even that few parameters are too many parameters to fully characterize a random process. So they just talk about what? Moments, especially second-order moments, especially autocorrelation function, cross-correlation function, complementary autocorrelation, complementary cross-correlation functions only, or covariance functions. And it's not easy. For example, consider the SETI project, Search for Extraterrestrial Intelligence. It has been a long research since 1960s, I remember, and recent Netflix series, what is Santi? That is also about Search for Extraterrestrial Intelligence project conducted by Chinese government. And what happens? Usually they do not send signal. Of course, they send signals, but usually they listen a lot of different frequency bands. And there are many different signals. So what do they do is that they calculate cross correlation between the signals in different channels. Of course, that separation of channels, definition of channels are arbitrary. So I really got angry when I knew that. But anyway, it started in 1960s or 50s. So we just admit that. Anyway, what do they do is that they take multiple signals from same source or something, and they take what? They estimate correlation functions, cross correlation functions. And if the two signals in different band have strong correlation, then it's an interesting phenomenon, and they search for more structure in the signal, something like that. Anyway, and also in financial signal processing, what is important is like this. Okay, last night, the US stock market, how to say it, boosted up a lot. What would be the probability that today's Kospi starts at some price and end the price higher than that? So you want to find correlation or correlation coefficient between some random process and some other random process, right? And if they show strong correlation, what can you do? You can earn some money, right? And these days, this financial signal processing has become so important. And unfortunately, this week, we lost one of the legendary mathematician and financial signal processor, James Simons, who founded the Renaissance technology. Probably you don't know, but Renaissance technology showed, one of their funds showed more than 41% compound, 41% compound rate. What does that mean? 41% means 1.41. That is square root of 2, right? What does that mean? After 2 years, your money doubles. After 20 years, it becomes 1,024 times. Got it? And the Renaissance Technologies so-called medallion fund had more than 41% compound rate for more than 20 years. What would that mean? Anyway, so many financial signal processes or they call quants, okay? Wants to find correlation between different signals in the stock market or in the world. And even they now use satellite images of some orange fields in Florida and orange fields in Brazil so that they can invest on the derivatives of the stock market. So they say that they buy the right to take the orange products in this summer. They sell something and they take money, something like that. Anyway, so here goes the correlation function. And then next topic would be estimation of correlation function. Of course, we are not too much talk about it. We are just, again, scratch the surface. But they may satisfy you already. So our 4 keywords, 3, but anyway, autocorrelation, cross-correlation, and other correlation type functions. Let's see it again. As I told you, the original definition of an autocorrelation function of a complex in general, complex random process is what? To use T1 and T2. So it's what? It's a 2-dimensional function. Here is T1 and here is T2. At each pair of point, T1 prime, T2 prime, you have a complex value. That is what? That is the correlation between x of T1 and x of T2. Of course, you have one more plane, and you take the same point, and you have what? Complementary autocorrelation between x of T1 and x of T2. Got it? If we define T1 as T plus tau and T2 as 2, then we have what? We have here T versus tau, or if you want tau versus T, depending on your preference. Got it? Now, let me remind you what is Y-sense stationarity. What is the consequence of Y-sense stationarity on this 2-dimensional autocorrelation function? First, if you use T1 and T2, just draw lines with unit slope. Got it? So on this line, what is common? T1 minus T2 is constant, right? So this is a line that shares the same time difference with this point. Y-sense stationarity means that if you have some value, function value, that must be the same on this line. Of course, on different line, the value may be different. Now, what about this case? What about this case? What if your autocorrelation function now parameterized by T plus tau and T? What would be the consequence of Y-sense stationarity? Whatever T you have, as far as tau is the same, the value is the same. So you draw straight lines with infinite slope and say that, hey, same value on this line. Something like that. Got it? Of course, different lines may have different values. Of course, not exactly because of the structure of this one. If you have propriety, then you have conjugate symmetry, blah, blah, blah. But anyway. Here goes one interesting definition, and that is a finite power process. So a random process, whether it is real valued or complex valued, is called sometimes a regular process or a finite power random process. This finite power random process is more easier to understand because by definition, see that? What is a power given a signal? Magnitude square. And if you take the expectation, that is the expected instantaneous power, okay? If this is a function of t and it's bounded less than infinity for all t, of course it's bounded and less than is a little bit different, but if this is always finite, then it is a finite power random process. Of course, this value could be a function of t. It is not necessarily a constant. Now, what about alternative definition of this finite powerness of a random process in terms of autocorrelation function? Now, let's little bit modify this one. Magnitude square of a complex number is simply what? Argument times its conjugate. And what is this? This is simply autocorrelation evaluated at the same time instant, t. Got it? So along the line that intersects this origin, what happens? Finite, okay? So you have some value, complex value in this case, real value is constant. Finite. That means you have finite power random process. Sometimes some people say that if a random process has finite ensemble averaged power, they call it second order random process. So it's very confusing. Some people call it a second order random process. Now, here goes some interesting definition of whiteness of a random process. Especially, let's consider a continuous time random process. What is white? What is the color white? And we believe, even though it is not exactly true, suppose here is the frequency range of a visible light. What is white color? It has components of all frequency components with equal strength. It's not exactly true, but mathematically, got it? So white means equal strength in the frequency domain. Got it? But this is only for visible light. What about white random process? Of course, in order to talk about this one, we need the notion of power spectrum. We haven't yet learned. We will cover that topic in the next chapter when we talk about the spectral characterization or characteristics of a random process. But just let's generalize. So whiteness, not just for a specific band, for every band, has spectrum like this, okay? For every frequency components, you have some finite power or something. What happens in the case? Just consider very, very high frequency, higher and higher frequency. What does that mean? Your signal can change very fast, right? Amazingly fast. What does that mean? if you take a sample at some time t0, and if you take a sample at time t1 very close to t0, what will happen? No relation at all, right? If you have a finite band limited signal, what happens? What does that mean? What does that mean? If you take samples at the Nyquist rate, then you may say that I have no idea what will happen. However, if you sample faster than Nyquist rate, actually, you can predict what will happen. Because relative to your sampling rate, signal changes slowly if you sample faster than Nyquist rate. However, there is no Nyquist rate here because it has infinite signal components. What will happen? Your sample taken at some point, T1, and your sample taken at T2. As far as T1 not equal to T2, what happens? Your, for example, expected value is 0. Or if you want, you subtract the mean, blah, blah, but mean is also irrelevant because the two values are totally irrelevant. So the idea based on the definition of this whiteness is this. Two samples taken at different value, different time instance is 0. But if you take at the same time instance, now what will happen? You may say that, okay, it may be a finite value because it's a variance. However, I said what? It has infinite components. If this is an energy spectrum, what is the energy of the signal? Infinity. If this is a power spectrum, what is the power of the signal? Infinity. What is the power, by the way? This is the power. So power is infinity means that if you take two samples at the same time, this value must be infinity. Then what kind of function is useful to describe this situation in electrical engineering? The direct delta function, right? If T1 minus T2 is 0, then you have infinity. If T1 minus T2 is non-zero, 0. That's why you have delta function. So here, a continuous time process x of t is white. Means in the time domain, the autocorrelation function is a function of T1 minus T2 through the direct delta function. So you have this fact. Now, what about this term? Is it necessary to have a constant here or some function of T1 and T2? In general, even though you have this property, you will have some non-negative function of T1 and T2, right? Because it's a function of T1 and T2. So apparently, it looks like your definition of white random process may require some two-dimensional function T1 and T2 times direct delta function of T1 minus T2. However, as you already know from the experience of signals and systems, if you have some situation like this, direct delta usually requires integration with respect to T1 or T2. In that case, what happens? Anyway, this will give you some value when T1 equals T2. So you can replace this factor as a function of Q of T1 and T1 or Q of T2 and T2 anyway. So this is actually a single parameter function. So by abusing the notation, this becomes the definition of whiteness over random process in the time domain. Okay, got it? So you have the definition. While and stationarity, we already defined, right? Now, let's see this example. Here, amplitude is constant. frequency is constant, but phase is uniform. You've already seen. The question is, what is the correlation, autocorrelation function of this one? And is it a function of time difference? And you already know that. If you compute the autocorrelation function as a function of t and tau, you have only a function of tau. So this deterministic random process, you remember that definition, right? This is perfectly predictable if you observe the sample path or realization up to some t0. You can perfectly predict the future. This random process is wise and stationary. It looks strange, right? Why? It's perfectly predictable, but you say that correlation is function of time difference. When I first saw this result, it was really confused me. Why? The reason is this. This random process is very special in that you only observe a single realization. Got it? You fix theta and then observe forever. So it can be perfectly predictable. But if you leave again and again and again, this infinite Big Bang to Big Crunch, infinite times, what happens? The random process is wise and stationary. So be careful. Wise and stationarity is not omnipotent. It's not that powerful. If your random process is, for example, deterministic or has some strange property similar to this deterministicity, then you have trouble. That's why we not only need wise and stationarity, but also ergodicity when we model some random process mathematically and when we handle statistically. Anyway, that is the topic of next class meeting. That's all for today.